Since the theory of electromagnetism was developed, it has been known that a charge moving relative to a current-carrying wire will experience a force, providing that the velocity of the charge has a component pointing in a direction that is parallel to the wire. The force experienced by this charge and the wire is a force that is proportional to the magnitude of the parallel component of the charge's velocity relative to the wire. It should also be noted that the direction of the force, whether it's attractive or repulsive, changes depending on which direction the charge moves along the wire. Einstein, upon his suspicion that this so-called magnetic force was nothing else but an electric field, published a paper entitled On the Electrodynamics of Moving Bodies. The ideas presented in this paper would be later known as the theory of special relativity. In this, he reconciled electromagnetics with mechanics by proposing changes, or transformations, to Newtonian mechanics. These transformations are real for all physical systems, but are most noticeable at speeds close to the speed of light. This allowed him, as will be shown, to explain the magnetic force in terms of its relativistic character, using only electrostatics. Suppose there is a current-carrying wire consisting of one positive and one negative line charge. The individual charges are assumed to be close enough together to allow this approximation. The positive and negative lines are moving in opposite directions, both at speed v, and the charge densities of these line charges are the same when observed from an inertial frame of reference in which the wire is stationary. This gives a net current in the direction of the positive charge, as shown on screen. Now, we will add to this picture a positive point charge, some distance away from the wire and stationary relative to it. This point charge will, from now on, act as our inertial frame. From this inertial frame, we observe two lines of charge. One is positive and the other negative. Both are moving at equal speeds, and the magnitude of their charge densities is the same. As non-relativistic electrodynamics will predict, this point charge experiences no electric force, as its perceived net charge of the wire is currently zero. However, electrodynamics also predicts that as this charge moves parallel and relative to the wire at constant velocity, a magnetic force will arise and force it closer to or away from the wire. So how can this be explained using only electrostatics? To do this, we will have to employ one of the Lorentz transformations. Briefly explained, this transformation states that if an object moves with constant velocity relative to an observer at rest, the observer will measure the object to be shorter than it would be if both the object and the observer were at rest relative to each other. Now, let's say that the point charge, our inertial frame, is moving parallel to and in the same direction as the positive line charge. Now, somewhat intuitively, we observe that the speed of the negative line charge is now greater than the positive one. Applying the effect of length contraction means that the negative line charge experiences more length contraction, but the amount of negative charge in the wire stays constant. Now, the negative charge density is greater than the positive one. This means that at any point along the wire, there is a net negative charge. Thus, our positive point charge will now experience an attractive force. Similarly, if the point charge does the same thing, but in the direction of the negative charge, the positive line charge will have a greater relative speed, and thus the experienced force will be repulsive. Originally observed from an inertial frame that was stationary relative to the wire, this force was called magnetic. However, by analyzing the situation from our new inertial frame, we can see that this magnetic force is in fact purely electrostatic.